Okay, so we're going to study the derivative as a function. The section before, we were asked to find the derivative at particular values of x. So let's just remember how to do that. If they ask me for the derivative of f at x equals 1, that will be the same thing as f prime of 1. Okay? This just means the derivative of f at x equals 1. So when they ask me for the derivative of f at 2, this is just the same as asking me for f prime of 2. Okay? I'm going to do it with both methods just to remind you that you can use either definition of derivative and it will turn out to be the same. So very quickly, for this one, I have this, and then I'm just going to apply my f here. F happens to be x squared, so I have 1 plus h squared minus f of 1 would be 1 over h. As I evaluate, the ones cancel out, and then I divide h by each term, so the limit as h approaches 0 of 2 plus h is simply 2. Now I'm going to apply the other definition of derivative, and I'm going to find the derivative of 2. So f of x is x squared, f of 2 is 4. I notice that I can factor out difference of squares, because if I evaluate 2, I get 0 over 0. X minus 2 as a factor is cancelled out, so limit as x approaches 2 of x plus 2 simply is 4. So that means, and going back to this small graph, the tangent line for 1 looks like this, and this slope is worth, as I said, 2, and the slope at 2 looks like that, and as a number numerically is worth 4. You notice how this tangent line is more inclined than that one, so it is logical that as a number is greater than the one here, okay? Or in other words, f prime of 1 is worth 2, and f prime of 2 is worth 4, okay? But the question for this section is, how can I find the derivative at every single x value without having to go through the trouble of finding it for every case? How can I find it as a function of x? How can I find it for any value of x? So this is what we're going to do now. Out of these two definitions, the only one that is useful for these purposes is this one, because in this case, this number is going to be my x. In here I make this number my x, then everything cancels out and it doesn't make sense to find the limit as x approaches x. So just for calculation purposes, we're going to use this definition to define what the function is. Okay, so for this definition, f of x plus h is x plus h squared, because that's what f does to anything that goes in for this example, minus f of x, which is simply x squared. When I simplify, the x squares are cancelled out. I have this. Then again, I distribute the h in each side. These two cancel out, and in here I get one h cancelled out. And now I can evaluate the limit by making h equals 0. So when I do that, the only thing that I have left is 2x, which means the derivative for f at any x value is going to be double that x value. Let's see if that was true with our examples that we have. When x was 1, I had the point 1, 1. What is the derivative at that particular point? The derivative was 2. When x is 2, the derivative here, this is the 0.24, the derivative was worth 4 as well, but that's just a coincidence because double of 2 is the same as 2 squared. But for any x, how can I find the derivative when x is 3, for example? When x is 3, how much would the derivative be? How much would the slope of the tangent line at 3 be? The rule says double of the x value, so it would be 6. I don't have to redo this for anything else. I'm just going to replace. I can answer questions like, what's the derivative of the function at 4? oh, well, 2 times 4, that's 8. I don't have to redo all this limit again because I know the derivative is double the x value, and that's a function, and I can find it for any x. Let's do it for the negative ones. When x is negative 1, I have this point. What is the value of the slope of the tangent line here? Well, easy. Again, double my x value, which is negative 2. I don't have to do any other calculations. So in that sense, this derivative is a function because it can be found for any value of x. Now look at this. The original function is a quadratic. The derivative is going to be a linear function. We're going to talk about later what are the relationships between f and f prime, or between a function and its derivative. Okay, so using the slides that I have given you, this just insists on the same idea. The derivative of a function at a particular value, you can use this definition, and then if instead of a particular value I want to use it for any value x that I want, then the function is defined as the limit of this ratio. So in here it says the function f prime is called the derivative because it has been derived from f by the limiting operation. So in example 1 here, this is a different exercise, but it works the same if I'm using my little car. The graph of function f is given in figure 1. Use it to sketch the graph of the derivative of f prime. I just duplicated the graph so that I can use this so that you can compare. So this is f, and I'm going to do f prime here. I'm not doing it right now. I mean, it's obvious that it's the same graph, but with pencil I'm gonna graph f prime. So again, the easiest thing to do is to find where the slope of the tangent line is 0. So I know that it's right here, and right here, and right here. So that's the easiest thing to do. So I know that it's going to be 0 at that particular value of x. So I know f prime has this point. It's also 0 to the right of 1. So right here is also 0. And it's also going to be 0 here. So I know the derivative as a number, the slope of the tangent line at those points are going to hit 0. Now what happens to the left of this 0? The slope is negative. So I know that it's going to be a negative value. What happens between this 0 and this 0? The slope grows, but then decreases. It becomes positive, and then it stops growing, and then it goes towards 0. So I know that it's going to be like that. Now from this 0 to this 0, I notice that all those tangent lines have a slope that is a negative, but it becomes negative, then it stops, and then it starts growing again until it reaches 0. So it becomes negative, it stops, and then it grows again until it becomes 0 again. Now from here on, the slope is just getting more positive and more positive as the tangent line is getting steeper and steeper. So I can just continue this. So you see the relationship between f and f prime. It has very little to do with the y values of f, and it has more to do with how fast it's growing. Notice how never mind.